Welcome also from my side. My role, or one of my tasks for this afternoon, for this session, is to keep you awake. Try not to fall asleep, and hopefully I can manage that throughout the next 15 minutes of my presentation. Title of my presentation is Key Dynamic Parameters that Influence Ride Quality of Passenger Transportation Systems. And whenever I talk about passenger transportation systems in the next 15 minutes, I'm going to abbreviate that with PTS. So when I talk about PTS, I mean passenger transportation systems, and these are elevators, escalators, as well as moving walkways. The agenda for the next 15-20 minutes, as shown here, I'm going to introduce the topic. We talk about components that affect ride quality, the dynamic interactions of those components. I give let's say, some kind of outlook into the possible improvements to improve, or measures to improve noise and vibration performance, and I'm going to conclude my presentation. First of all, general introduction. All humans, if I look to the audience, it's obvious, all humans are different. And so the perceived performance of a PTS ride, either vertically using a lift or horizontal using a moving walkway, or with an escalator in horizontal and vertical direction, is not the same. A PTS contains of a large number of components which interact with each other. These components influence the ride quality of a system, and it is of interest of a PTS manufacturer to install and run a system that makes the PTS ride, as smooth as possible. Let's define ride quality. What is ride quality? Ride quality is a measure of the comfort level experienced by the passengers, and again, that's subjective. It is intimately associated with the subjective perception and sensitivity of motion and to sound of a moving lift car in this case. It uses the following parameters: vibration, and in vibrations we talk about three directions, X and Y, and the Z direction, acceleration and jerk, and sound pressure level and tympanic pressure. Let's talk about human discomfort. And as mentioned, if I look into your faces, we are all different, so the unique response from everybody to the multiple facets of ride quality is different. The application of sound and noise vibration, the application of noise and vibration to a human body can create various subjective effects of human discomfort. And in my next slide, I'm going to talk about what that could be. If it comes to extremes, noise and vibration, especially vibrations, can cause stress effects. It's common practice in our industry to work to certain limits, and my intensive literature research came to these results. So if we stay in certain limits for critical ride quality, this ensures a good ride quality. If we, for example, are able to ensure jerk rates under 1.0 meter per second to the power of 3, or travel distances below 400 meters, because everything which is above 400 meter travel height is can cause uncomfortable feeling of the passenger. If we talk about, sorry, where's the laser pointer? Thank you. For example, if we talk about speed, everything below 7 meters per second is assessed by the passenger as an acceptable speed. Acceleration rates from 0.8 to 1.6 meters per second square improve passenger comfort. Horizontal vibrations are typically specified below 25 milli-G, and if the PTS, for example, the elevator cabin, if this maintains a maximum sound level of 55 dBA, this is a desired limit we are looking for. So far I talked a little bit about noise and vibration, but let me talk about the human frequency band for a minute. Humans can hear frequencies between 20 and 20,000 hertz. However, there are substantial, let's say, variations between individuals, especially with high frequencies. The sensitivity for noise also varies with frequency, and the noticeable range of vibration for human being is even below the minimum of hearable noise. So when we talk about vibrations, this is below the band of human frequency. Coming back to the title of my presentation, so I wanted to talk about the key parameters that influence the ride quality. So you may ask what components of a lift system or PTS affect ride quality. So I prepared this slide for you. Vibration sources affecting lift car. Now, vibration sourcing affecting lift car involve the following: car guiding systems, suspension and compensating ropes, and airflow. And I know that there are specialists in the audience. This is not new to us. In my paper, I didn't look into the effects of airflow because that was a bit too much for this for the paper. However, if you are interested into more details of the investigations I made together with the University of Northampton and Stefan Kaczmarczyk and Rory, please refer to the paper which is in the conference book. The underlying causes of vibration vary, and they include imperfection of guide rail and joints, eccentric pulleys and sheaves, systematic resonance in the electronic control system, and of course gear and motor generated vibrations. What is dynamic interaction? And the investigations we made prove that it's the physical effect of resonance that cause issues with noise and vibration in PTS, so in passenger transportation systems. Let me explain the physical effect of resonance real quick on a high level. If we talk about primary external resonance, it's defined as a system acted upon by a periodic force or excitation that will experience resonance if the frequency of this force coincides with one of the natural frequencies of the system. And to explain this, I put together this little drawing, and here you can see how this works. So here in this case, the natural frequencies of this is the same as that, and therefore this excites that, and in this case it doesn't work because the frequencies that do not match. All this, what I've shown you so far, is the explanation for the case study I want to present to you, which is the, let's say, the core of the paper we put together. And it's a given system with this specification. Rated speed of that system is 1.6 meter per second with a travel height of about 24 meters. And however, the system has shown a vertical vibration of over 58 milli-G. And the investigations we did together with the University of Northampton has shown that the fundamental frequency of the response was about 3.25 hertz, which was close to the frequency of the rotational speed in the diverter pulley, which was determined as 3.18 hertz. By the way, this was a 4-to-1 rope system. We put this into a model, simple model, which you see here, but I don't want to bother you with too much of details. I tried, and not to have any formula in this presentation, by the way. If you're interested in this, it's all in the paper. But let me draw the attention to the, let's say, summary in blue. So the dynamic interaction between the pulleys, the suspension and lift car, in our case, were responsible for the compromising ride quality of that specific system. Now we ask, or you can ask, how can we improve this, this poor ride quality? And there are basically three basic principles which improve the performance of noise and vibration emission. First of all, prevention, decoupling, and damping. Prevention is defined as to reduce the strength of the source. When we talk about decoupling, it means to interrupt the noise and vibration path. And damping is defined as to absorb the energy generated due to noise and vibration. For those of you who know me better and who worked together with me, they know that I like being in England, and one of my hobbies is our classic motorbikes. And I was looking for an example, practice example, to explain you what can be done if it comes to, let's say, excessive vibration in a system. And I found an example in the motorcycle industry, and this is a picture of an English motorbike built in the late 1960s. This is a Norton Commando, which was introduced into the market in 1967. And they came up with a new isoelastic frame, and this was a technology that made, at the end, the ride of their motorcycle much smoother and comfortable. And how did they do that? They just added a rubber ring into the frame here, where the engine is mounted to the frame, and all the vibrations coming from this from the motorcycle engine was not anymore, let's say, doesn't move into the frame and into the driver. The next two slides, I'd like to conclude my presentation. PTS ride quality technically defined in terms of technical details such as physically measured noise and vibration parameters. In some cases, excessive vibration might lead to failure of the design components and will compromise in passenger safety, and we talked about passenger safety yesterday, so this is definitely something we need to look into and have always have a focus on. Excessive levels of noise and vibration may cause multiple and possible severe damage to the human physiological subsystems. And in my paper, this is even detailed out more, what that could be. PTS ride quality is affected by various sources of excitation, which are related to elements such as rails, rail joints, roller guides, or imperfect rotating components or ropes. And the most critical phenomenon affecting ride quality, and some of you are experienced in this as well, is resonance, as this often leads to instability of the vibrating system. Before I open the question round, I'd like to give you an outlook why I present this to you and what comes next. Basically, what I put together with the paper is the first introductory part of a comprehensive research project with the University of Northampton with the School of Science and Technology. The company I'm working for has a cooperation with the University of Northampton, but as well as we do a cooperation on a working level with the University of Stuttgart. And we look into advanced technical details in regards to advanced vibration damping of rope-free elevator systems. But there's another topic which I'm really interested in, and I investigate. This has to do with pedagogic principles and adult learning. So the main research, my main research, looks into concepts of learning, adult education principles, applied problem-solving strategies, and its implication to the concept of a Master of Science course for the University of Northampton. At the end of the day, I will come up with I will develop a new design concept for distance learning, for a distance learning course to enhance higher engineering education in the multicultural, multidiscipline R&D environment of ThyssenKrupp. What I presented here and the outlook, what I just presented a minute ago, this all is the foundation of a new ropeless elevator system we are working on. And we are using, the research team in Germany uses high computing simulation for ride quality investigations in regards to building sway and cabin-to-cabin interaction. To demonstrate our results, our research results, we use 3D visualization. And I'm sure that 100% of you have already seen that we prepared something for you. We have a booth at in the back of the room, and I'm sure that most of you have already experienced what we have there. However, if you are interested in this 3D visualization, please refer to our team. We have 4 guys working for us at the booth in the back. Yeah, and this is basically it. That's the end of my presentation. I'd like to thank you for your attention.